This is Chapter 15. It is broken into two sections. In today's section, we're going to be looking at aqueous solutions. We're going to also focus on four different equations dealing with hydroxide and hydronium ion calculations, pH and pOH. To start off with, so self-ionization of water, it's where you have two water molecules producing a hydronium ion and a hydroxide ion by the transfer of a proton. So you can see your two water molecules coming together to produce both of those. I will say self-ionization of water, that is a reversible reaction, and a very small amount of water does self-ionize. If we look at water basically at room temperature, about 25 degrees Celsius, you can see that the concentration of hydronium and hydroxide ions is both 1 times 10 to the negative 7th molar. So again, concentration, we are looking at molarity here. And there is our equation. So this is the first of several equations that you'll be introduced to today, and you will need your scientific calculator. The brackets that you see around both of these, that is saying the concentration of, so concentration, we're dealing with molarity, the concentration of the hydronium and hydroxide ion multiplied together gives you Kw. Kw is the ionization constant for water. It is the ionization constant for water. And if you look at both of these and you multiply them together, we are looking at 1.0 times 10 to the negative 14th molar as far as your ionization constant for water. So 1.0 times 10 to the negative 14th. That is taking 1 times 10 to the negative 7th and 1 times 10 to the negative 7th and multiplying them. Just as a reminder for exponents, when you're multiplying exponents, you add exponents together. So negative 7 plus a negative 7 equals negative 14. So just trying to make that mathematical connection for you. So there's that math connection again for you. Kw, so the ionization constant for water, it does increase as your temperature increases. So this chart is showing you a few different temperatures. And as temperature increases, you can see that the constant also increases. When you have your hydronium and hydroxide ion concentrations equal to each other, then you have a neutral solution. If hydronium is greater than hydroxide, you're looking at an acidic solution. So hydronium ion concentration is greater than 1 times 10 to the negative 7th molar. And if hydroxide is more than hydronium, then you're looking at a basic solution. Again, the acidic solution or acids typically produce the hydronium ion. Basic solutions typically produce the hydroxide ion. Acids have the hydrogen ion. Bases, like your sodium hydroxide, strontium hydroxide, potassium hydroxide, all have the hydroxide to give you the basic solution. So all that stuff we learned in Chapter 14, we're shoving into Chapter 15 now, and we're using those into calculations. Strong acids and strong bases are considered completely ionized or dissociated in a weak aqueous solution. So there's your sodium hydroxide, which is a strong base that is dissociating. And this one right here, if you had a solution that is 1 times 10 to the negative 2 molar sodium hydroxide, you would write that value. This is an important connection. If it is written like this, then you are saying the hydroxide ion solution is equal to 1 times 10 to the negative 2 molar. So trying to fit that into the equations that we're looking at, that's what you have here. Hydronium ion concentration of the solution, if you had to calculate it, so your Kw equals 1, or the hydronium times hydroxide ion concentration, which is equal to 1 times 10 to the negative 14th. If you plug in those values, can't see those very well. But if you were to plug in those values, rearrange your equation to get the hydronium ion concentration by itself, your final answer, and I think that is a typo there too, should be 1 times 10 to the negative 11th. Let's go work it out together. And that was not a typo on that one. I was looking ahead at my next slide that I believe has a typo on it. So if we're looking for the hydronium ion concentration, and if I rearrange this, hydroxide must be brought over, and it will be divided on the other side for OH. So hydronium ion concentration is going to be equal to 1 times 10 to the negative 14th divided by the hydroxide ion concentration for that problem was 1 times 10 to the negative 2. And so our answer is 1 times 10 to the negative 12 molar. 1 times 10 to the negative 12 molar. So they're reversing the calculation on this next example. If the hydronium ion concentration is known, then hydroxide can be calculated. So let's say that you know the concentration of hydrochloric acid, which is a strong acid, is 2 times 10 to the negative 14th molar. And that makes the hydronium ion concentration 2 times 10 to the negative 4th molar. You plug that into this equation, rearrange it to get hydroxide all by itself, and you make your calculation. Again, on this one right here, we have, if you were to do the original math, again, you're in your scientific calculator, so it's great, but the math right here is actually equal to 0.5 times 10 to the negative 10. That's where I was saying the typo is, because if we move our decimal, and your calculator does this for you to get it in proper scientific notation, when we move that to make a half become 5, then we have to change our exponent. We took one away, or added 1 to this side, we must take away from that side. And so our final exponent should be negative 11. So 5 times 10 to the negative 11 molar is our final answer here. So this one right here is throwing in some acids, conjugate acids, bases, conjugate bases, and it's giving you the K value for each of these. So Ka is going to be for the acid, and we're just looking at some of them. Increasing acid strength, increasing base strength, if you were watching out for our sides over here. So increasing acid strength as you go up, increase in your base strength as you move down. So we did look at strength of acids and bases in chapter 14. This is giving you some actual Ka values now so that you can compare. If Kb values were given for the conjugate base side of things, again, you would see that those values would go in the opposite direction. And in this chart right here, again, it's just giving you some examples. If you had pure water and then strong acid, strong base, and it's changing up the concentration for you over here to the side. It's giving you the hydronium hydroxide ion concentrations, and if you were to multiply each of these on the way down, then you would get a constant value for your ionization constant for water, which is 1 times 10 to the negative 14th. So write down this example. We're going to work through it. A 1 times 10 to the negative 4 molar solution of HNO3 has been prepared for a laboratory experiment. It is going to want us to calculate the hydronium ion concentration of the solution and the hydroxide ion concentration of the solution. Now this HNO3 is nitric acid, which is a strong acid. Since it is a strong acid, it will completely ionize. Therefore, since this completely ionizes and there's only one hydrogen in this strong acid, the molarity given originally is the hydronium ion concentration. So H3O plus is going to be equal to 1 times 10 to the negative 4th molar. So that is the hydronium ion concentration. So no calculation needed for that first part, but now we're going to go calculate the hydroxide ion concentration. So I've already got this one worked out. I have just rearranged the ionization constant for water equation to get hydroxide ion concentration by itself. I've plugged in the value that we knew for nitric acid, that's its hydronium ion concentration, made our calculation. So the hydroxide ion concentration is 1 times 10 to the negative 10. Again, since this is an acid, I would expect hydronium to be more than hydroxide, and it is. Moving on over to the pH scale. pH. The pH of a solution is defined as the negative of the common logarithm of the hydronium ion concentration. And there's your equation. pH equals negative log of hydronium ion concentration. You're definitely going to want to write that equation down. pH comes from a French phrase meaning hydrogen power. So pH is why we have that. That is a lowercase p and a capital H written just like what you see here. A neutral solution of the hydronium ion concentration is 1 times 10 to the negative 7th. If you take the negative logarithm of that, or the logarithm of it, you get negative 7, and then take the negative way, you get 7. So you can plug in a neutral solution into this equation, and you will get a pH of 7. So on the pH scale, 7 is considered to be basically in the middle. We will look at the pH scale again on the pH scale that we'll get to in more detail. 7 is essentially the middle. 14 is typically the one end. 0 is the other end. We would say acids are going to be from 0 to 7, and your bases are going to be from 7 to 14. And this one right here, it's giving you some different solutions. So if you just have straight water, great. pH is going to be 7 once you do your calculations. So it is going to take these values and do the calculations in the equation that we just showed you. They're taking, both of these are acids, which is HCl, so we expect a pH below 7. And the next one, we've got NaCl, which is a salt. Salts are typically neutral, so a pH of 7. And then in the next one, next two, we have a base, sodium hydroxide, so we would expect pHs above 7 since both of these are bases. And here we have an equation for POH, so it's going to be your hydroxide power. This POH is negative log of the hydroxide ion. So again, they're taking the same example. If you have a neutral solution and the hydroxide ion concentration is 1 times 10 to the negative 7th, the pH is definitely 7. The negative logarithm of this is going to be 14. So pH plus POH equals 14. So we have 2 more equations for you to write down. I'm going to go ahead and show you the 4 main equations for this section. So here are those 4 equations all together, just making sure that you have them down. We will be working through several problems within this chapter, and you'll be using one or a combination of these equations to get your calculations depending on how the question is asked. So again, anytime you're doing calculations for me, if there's an equation that you're using for the base of your calculations, which there should be, please show all of your work. So we are going to look at this right here, and I'm going to add some stuff to it, just trying to make some connections for you. I'm going to add some examples too. So let's go ahead and start with our examples. On the acid side of things, right around a pH of 5, we're going to have coffee. Just giving you an idea. Apple juice is going to be right over here. And again, if you have your normal acids that we've talked about, they're going to be on the acidic side of things too. Bases, right over here about 8 are your antacids. These are things, let's say that you have an upset stomach and you know there's acid in your stomach. If you want to neutralize that acid, then you need to put a base in there. Hand soap is going to be right about here, so hand soap. And then ammonia, which I know you've heard of, ammonia would be right in this area. And then obviously the bases we've talked about, which ammonia is a weak base. But your strong bases, the sodium hydroxide, potassium hydroxide, barium hydroxide, those would all be even higher on our pH scale. Again, pH is listed here 0 to 14. So you do have this to look at, and there's the hydronium ion concentration. Notice that your values match up. So a pH of 0 is 10 to the 0. A pH of 14 is 10 to the negative 14. A pH of 5 is 10 to the negative 5. So there is some correlations if you're directly on a whole number between the pH and the hydronium ion concentration. Let's go in and add just a few more examples before I get to POH. Battery acid is going to be right in this area. So battery acid. Your stomach acids are also going to be in this area here. So that's stomach acid. Baking soda, which I know you're familiar with. So baking soda. Right in here. Drain cleaner. Drain cleaner is going to be on this end of things. So drain cleaner right there. So getting to our POH. Just trying to change up some colors. If I were to look at POH, then these numbers 0 to 14 would be backwards. You would have 14 on this end, which is the left, 0 on the other end, still your 7 in the middle. So this would be 7, 8, 9, 10, 11, 12, 13, 14. Moving to the right, 7, 6, 5. This would be 4, 3, 2, 1, 0. So you can see your POH values. If you were looking at hydroxide ion concentration values, then this would be 10 to the negative 14th because your POH is 14. This would be 10 to the 0 since your POH is 0. Still 10 to the negative 7, but if I added some of these others, 10 to the negative 4 for some of the numbers that I added up top, 10 to the negative 10 over here. Again, if you're on a whole number, then these values are really easy to calculate even without a calculator as long as you're making those connections. Here are even more examples that I would just say in general, be familiar with them, kind of know where they fall. So just wrapping up some of the equations we looked at, if you're neutral, pH equals POH, hydronium ion concentration equals hydroxide ion concentrations for neutral solutions, and then there's the actual values that you have. Acidic solution, hydronium is more than hydroxide ion concentration, pH is also going to be lower. And then for basic solutions, hydronium is less than hydroxide ion concentrations, and pH is going to be higher if you're talking about basic solutions. This is just a quick note on significant figures. The rule is it's supposed to be as many significant figures to the right of the decimal as those found in the logarithm. So this one has one significant figure in the example, so I have one decimal place shown. If you show me a minimum of one decimal place plus anything before the decimal in your answers, we should be good. If you need to write down these directions on how to do these calculations in your calculator, feel free, but I will explain it as we go through some examples. So let's look at this example. What is the pH of a 1 times 10 to the negative 3 molar sodium hydroxide solution? Please write it down and then all the work that we show. So as I look at this, I note two things. Number one, at the very beginning, the material that I have information for, that is a strong base. So it will dissociate completely, but since it's a strong base, it dissociates into hydroxide ions. So that concentration given is the hydroxide ion concentration. It is asking for pH. pH is related to the acid side of things. So since I have information about a base, but it wants information from the acid point of view, I know that this is going to be at least 2 different steps. So if you are looking at all 4 of your equations, so look back at all 4 of your equations, typically these could be done in 2 different ways, depending on which equations that you start with. For me, I'm going to start with the ionization constant equation, which is 1 times 10 to the negative 14th, hydronium ion concentration plus hydroxide ion concentration. So once I put in my hydroxide ion concentration, just erasing that, writing it a little better, I can get my hydronium ion concentration, and then after I have that answer, I can go back and find pH using the negative log of the hydronium ion concentration. So those are the 2 equations I'm going to choose to answer this. You could have also went with this information for POH equals negative log of hydroxide ion concentration. And once you found the POH, you could have said pH plus POH equals 14. Again, with those 4 equations, typically how this works out, you'll need 2. It's not uncommon to need 2 to answer, and that means you'll have multiple avenues to go about it. So I'm going to go back to the original way I was going to work this one out. So 1 times 10 to the negative 14th equals hydronium ion concentration. I'm going to go ahead and bring hydroxide over and divide it. Since this right here just has 1 hydroxide ion, then I know that concentration is 1 times 10 to the negative 3. And when I solve for hydronium ion concentration, I get 1 times 10 to the negative 11. Now I will plug that answer into this equation and solve for pH, which is negative log of 1 times 10 to the negative 11. Putting this into my calculator, you should be able to just put in 1 times 10 to the negative 11. It might need to be in parentheses. It depends on your calculator series. Press the log button. Log might have to be hit first. Again, it depends on your particular one. I have a TI-83 that I am working with. So when I hit the log button, automatically parentheses come up. So I'm doing 1 times 10 raised to the negative 11th power. Closing my parentheses, I get a negative 11. And if I take into account the negative at the beginning of this, then that brings it back to a positive 11. So your pH is equal to 11. 11. So here we have another example. Make sure you write it down. This one wants to know what is the hydronium ion concentration, which is H3O plus, if you have a pH of 4. Well, with this equation, pH equals negative log of hydronium ion concentration. Looks like we can do just one equation here. And with this, I will plug in 4.0 equals negative log of hydronium ion concentration. Now, when I take negative log, this was what was described earlier that I said I will verbally tell you what the math is. If I want to get H3O by itself and negative log goes to the other side, we call that the negative anti-log. In your calculator, though, if you see your log button right above the log button, and mine is in yellow, it's 10 to the X. So if I hit my second button and log, 10 raised to a power comes up with the parentheses, and I will type in 4.0. but it needs to be negative 4.0 because I've got to bring my negative over. So again, second log, negative 4, and we get an answer that is 1 times 10 to the negative 4th. 1 times 10 to the negative 4th. Make sure when you put that in, and I said make sure you put in negative 4, that you don't use your minus sign for subtraction. You actually use the negative sign on your scientific calculator. So again, bringing over a log is called the antilog, and it is second log on your calculator. So this is the final answer to this question. So we've got the relationship between hydronium hydroxide ion of some different solutions. Again, if I'm noticing bases and acids, here's a base here. That's a strong base. At the bottom we have a weak base. And then we have a weak base also with NH3. So that's a weak base. And then you have a strong acid here with HCl. Oh, and I said that wrong. CH3COOH. That is a weak acid. I'm sorry. So acetic acid at the bottom is a weak acid. So we got our two bases at the top, strong and weak. Two acids at the bottom, strong and weak. And you can see that the pH of solutions of weak acids and weak bases have to be measured experimentally. They're not going to be as easy as your strong acids and strong bases. So they will have to be found out experimentally. And this is just wrapping up some of the ones that I had showed you earlier, where they fall out on your pH scale, what is considered more acidic and more basic.